Hi, this presentation will give more details about how a texture image is applied to a portion of the screen for rendering. And in particular, we have problems with aliasing. So the problem is that the texture map is in a rectangular array of pixels, say holding, for instance, color data, and the screen is a rectangular array of pixels, which will be the colors displayed at the end for each pixel. But there may not be a one-to-one correspondence between the pixels in the texture map and the pixels on the screen. And we have to deal with that in some way. And the two methods we're going to talk about in this presentation are bilinear interpolation and mipmapping. And these are chosen for this particular presentation because they're the two methods that are natively supported by OpenGL. So they're very easy to implement in an OpenGL program because they're just a built-in part of the OpenGL pipeline. So let's draw some pictures here just to get started. Here I've got some texture map, which is a rectangular array of pixels. And I'll just draw it just as a 3x3 array of pixels. And I'm going to put black dots at the center of each pixel. So here I've got 9 pixels total shown. And the black dots are the centers of the pixels. And we sort of think of the colors of each pixel living at the center of the pixel, and the overall texture map is an approximation to a smooth image of some type, a continuous image. And the screen also is a rectangular array of pixels. And let's see here, let's draw this as, I'll do a 5x4 array of pixels just to be different. And each screen image, when we're drawing, say, a triangle and taking texture coordinates out of the texture map, we're picking each pixel in the screen, and it's going to have some texture coordinates assigned to it, coming as averages of texture coordinates from the vertex attributes. In this case, maybe it's S0 and T0. And as such, S0 and T0 so S goes from 0 to 1 from the right side from the left side to the right side of the texture map, and from 0 to 1 from the bottom to the top of the texture map. And S0 and T0 will sit somewhere in that interval 0 to 1, say, and will correspond to some point in the texture map, which in general will not be a texture center. So basically what's happening is, what we do in this case, we're sort of thinking of the pixel on the screen image corresponds to some somewhat rectangular region, but not exactly rectangular region in the texture map. So the texture coordinates can be all skewed. They don't have to correspond in a rectangular way. And so the screen image pixel, the center of it sits here, right? If we took the whole pixel, it sort of occupies some patch of the texture map. And what we would like to do now is to assign some color to the pixel from these. And the typical method that would be used to make this work well, there's two methods. One is we could just go to the closest, sort of snapping to the closest pixel in the texture map and just use that color. But that's obviously going to cause some problems. A better way to do it is to bilinearly interpolate between these colors. So we take this one here, these 4 colors, and we're going to take a bilinear interpolation. Well, bilinearly interpolate 4 pixel colors, I'll call them, but it could be other values from the texture map. And the bilinear interpolation is controlled by parameters alpha and beta. And of course, the alpha is going to be the left-right sitting inside the square formed by these 4 pixel centers, and the beta will be from bottom to top in the same square. So this actually works pretty well, but it does have problems. It especially works well if the resolution of the texture map is similar to the resolution of the screen. It can have problems if the texture map is higher resolution or lower resolution. But this method, this method of bilinear interpolation works well if the resolution of the texture map is either the same or lower than that of the screen. So if the resolution is similar to or lower than the resolution of the image in the screen. So it seems pretty clear that it ought to work relatively well if the resolutions are similar, but it also works as well as you could expect if the resolution of the texture map is much lower than that of the screen. What that would mean is that you have what that would mean, though, is one pixel on the texture map would correspond to a bunch of images on a bunch of pixels on the screen. And so you would get a sort of chunky picture on the screen where one pixel would be coloring a lot of contiguous pixels on the screen. It looks sort of chunky, but in some sense that's about the best you can do, right? So that's okay. And the OpenGL commands for this, I can give this to you. Let me stop talking for a moment for you. So here's the OpenGL command for enabling this type of bilinear interpolation. So this enables bilinear interpolation. And what do the different parts of this mean? It says it's applying to 2D texture maps, which is the usual kind of texture map. And, correct the spelling error here, this is MAG. GL texture mag filter, GL linear. So mag means we're making the texture map pixels bigger, magnifying them. And so this applies to the case where the resolution on the texture map is smaller than the resolution of the screen image. And it says the GL linear means use the bilinear interpolation. They use GL linear, but they mean bilinear interpolation. The other option in the default is GL nearest. GL nearest instead of GL linear would just snap to the nearest color and use that instead. Easier to compute, but doesn't give as good results. So this is the case that works pretty well when the texture map has the same resolution or lower resolution than that of the screen. So the next method is going to apply to the opposite situation where the texture map has higher resolution. So the problem turns out to be worse if the texture map has higher resolution than if it has lower resolution, and which is sort of counterintuitive. It would seem like the trouble with low resolution texture maps was you didn't have enough information about the image to properly paint detail onto the screen. And you get a very low resolution looking image on the screen, large pieces with little detail built in. But actually the higher resolution texture maps are harder to deal with than the lower resolution texture maps. So this picture is something like the following. We've got a high resolution texture map here with lots of pixels. Try to draw lots of pixels here. And then we've got a lower resolution screen with relatively few pixels. Maybe it's a 3x3 array of pixels on the screen. Let me mark the pixel centers here. And now you'll notice that if the texture map is being mapped into this, each screen image is going to have each screen pixel is going to have a pre-image, which, let me just draw this over here. Maybe the pre-image of this first pixel is here, right? So think of that as corresponding to this one. Maybe the next one is here. And maybe the next one, maybe it's dropped down a row to here, right? So, because there doesn't have to be a linear relationship between the pixels. So that might be the top ones, and the next three might be here, and the next three might be here. And if we just did either snapping to the nearest pixel center or using bilinear interpolation, even with that, we're still only picking up a very small number of pixels in the texture map are affecting the pixels on the screen. A lot of pixels are being missed. And even worse, if there are patterns, in the texture image, for instance, if there were horizontal or vertical stripes, e.g. horizontal or vertical stripes, for instance, but it wouldn't have to be just that kind, then the image that you see on the screen might depend very heavily on exactly where the pixels landed in the texture map, or the pre-images of the pixels landed in the texture map. And if it's animation, you may actually get all sorts of flashing, whereas the texture map moves across the screen, the pre-images of the pixels picking up data out of the texture map may move in a uniform way between, say, brightly lit areas and unbrightly lit areas and so forth. And you can get all sorts of bad effects, especially with aliasing. So you can get very bad effects. Especially with aliasing, especially with animation. So you can get very bad effects, especially with animation. And so this is a problem, and it's hard to work. What we'd really like to do, but is hard to do, what we really want to do is we want to take a pixel, say this first one here, and take its pre-image on the texture map. Maybe it's some region like this, right? And then we want to take the average color of all the pixels in the pre-image of the screen pixel and use that instead of just choosing a couple small pixels. So we'd like to get some method of doing that. So I'll describe a method that gets you partly there on the next slide, called Mipmapping. But the ideal would be a pixel in the screen image corresponds to a patch of the texture map and the pixel on the screen, and the screen pixel gets the average color from that patch. That's easier said than done, but I'll describe next Mipmapping, which is a way that partially solves this problem. So Mipmapping is, the word Mipmapping, MIP, stands for a sort of fake Latin phrase, multum in parvo, or something like that, many parts. What it does is it pre-processes the texture map down to lower resolutions. So you pre-process copies of the texture map at lower resolutions. So the basic idea is the following. You start off with the initial texture map. And let's assume it's n pixels by n pixels. So it's n squared many pixels altogether. And what we're going to do is we're going to shrink it in size successively. We're going to take that n by n array of pixels and make a new smaller texture map, which has n over 2 pixels by n over 2 pixels, so it's n squared over 4 pixels total. And we do this by taking successive blocks of 2 by 2 pixels in M in the texture map and mapping them by averaging to a single pixel in the next mipmap level. So this is the base level of the mipmapping, and we split it up into 2 by 2 subpixel regions, and each of these 2 by 2 subpixel regions maps to a single pixel by just taking the average of the 4 colors in the 2 by 2 subpixel in the original texture map and assigning that as the pixel color in the next level of the mipmap. And then we repeat this. We go to n over 4 by n over 4, so this is n squared over 16 pixels. And we just do the same process again. We have a 2 by 2 array of pixels in this level, and it maps down to a single pixel with the average of the colors from that 2 by 2 array in the next pixel. And we repeat until we hit a 1 by 1 array of pixels. And then we're done. And that gives us, each one of these is called a mipmap level. There's the original level, the next level, the next level, and so on. And you'll notice that then what we do is then we, when applying a texture map to the screen image, to the screen, what we do is we look at the resolution of the screen versus the resolution of the texture maps, and we do the following. We either pick the mipmap level that is closest in resolution to the screen image, and then we can still again use bilinear interpolation before, and use bilinear interpolation to pick the screen pixel color. But now it's using bilinear interpolation just on the mipmap level that's closest to that of the screen. Or we can pick the 2 closest mipmap levels in resolution. So we pick the two mipmap levels. Closest in resolution to the screen. And then we do the bilinear interpolation on both of them separately. And then linearly interpolate between the 2 results. So again, when we're mapping to the screen image, let's put the screen up here for a moment here. Here's the screen image. With the screen image, we have S0 and T0 values for the texture coordinate. I shouldn't write up here. So here's something here with texture coordinates S0 and T0. That would correspond to some place in the original map, but likewise to the same corresponding place in all the mipmap levels. And we would just pick either the closest in resolution mipmap level to the screen image, or the closest two that bracket it, one slightly above in resolution and one slightly below. And we would then use, for each picked mipmap level, we would do bilinear interpolation on the pixels inside, the 4 closest pixels inside that mipmap level. That gives us 2 values if we're in the second scenario. And if we have 2 different mipmap levels, then we would linearly interpolate between those 2 results and give that as the color or whatever value we're using for the screen image. So this is particularly useful if, for instance, we're panning into a surface. So if we're animating and say the camera is moving closer and closer to a surface, the surface may start off very distant, and so we would use the low resolution mipmap level. But as we get closer and closer to the surface, more and more of the screen is taken up by the surface, and we would transition smoothly to the next mipmap level and the next mipmap level and so on, always working with versions of the texture map that have resolution similar to what's being shown on the screen. And this can work very well. There's certainly places where it doesn't work so well. One is if you're looking at a surface that at a sharp angle, then the resolution maybe in the X direction could be very different than the resolution in the Y direction. And so, OpenGL does its best with it, but it's not going to be perfect. That's a hard problem to fix with this method. So basically, you just try to keep those effects as minimal as possible. So to finish up on the next board, I'll show you the OpenGL commands that do this. So here's the version of the command that sets the parameters to use the most amount of interpolation and mipmapping and so on. So it's the GL tech parameter I command where it's applying to 2-dimensional textures. The GL texture min filter, before we had mag filter, min filter means that it applies in a situation where the texture map has higher resolution than that of the screen image. The GL linear part, this means use bilinear interpolation as described earlier, namely each pixel in the screen image picks up 4 colors from 4 pixels in the mipmap level image and uses bilinear interpolation between them. And this says to use 2 mipmap levels and linearly interpolate between them. The other options here is you could use GL nearest mipmap linear, which would mean don't use bilinear interpolation, just snap to the closest pixel. You could also use mipmap nearest to mean just use 1 mipmap level, not to linearly interpolate between the results of 2 mipmap levels. Or you could just leave off the mipmap linear and mipmap nearest part completely, and then it wouldn't use mipmap levels at all. So I will discuss in another video the rest of the OpenGL commands that are used for texture mapping, but these are the ones that control the parameters I've just talked about now. So the next presentation will talk about yet another technique for handling the situation where texture maps have higher resolution than the screen image. This will be called supersampling or stochastic supersampling. That is not supported in OpenGL, and it'll wait until the next presentation. That's the end of this presentation. Thank you very much.